Have you ever stared up at the night sky and wondered just how far away those twinkling points of light really are? Tonight, we're diving into one of the most mind-bending concepts in all of astronomy, a measurement so vast, so incomprehensibly huge, that it literally breaks our ability to understand it. We're talking about the light year, and I promise you, by the end of this journey, your perception of distance will never be the same. I'm so glad you're here with me for this exploration into the depths of space and the limits of human comprehension. Feel free to settle in, get comfortable, and prepare to have your mind stretched to its absolute limits. The visuals are here to guide you through this cosmic journey. But there's absolutely no problem if you find yourself drifting off as we explore these vast distances together. Sometimes the most profound truths are best absorbed when our minds are relaxed and open to wonder. Before we launch into the infinite, I'd love to know where you're watching from tonight. Drop your location in the comments below. Are you gazing at stars through your window right now? Maybe it's morning where you are, with sunlight streaming in to remind you of our nearest star. There's something beautifully poetic about discussing cosmic distances, while we're all scattered across this tiny blue marble we call home. Now, imagine for a moment that you're standing in the middle of a vast desert. You can see in every direction for miles and miles until the horizon curves away and disappears. That feeling of enormous distance, that sense of vastness that makes you feel small and insignificant, represents just a few dozen kilometers. Hold on to that feeling, because we're about to multiply it by trillions. The light year isn't just another unit of measurement. It's humanity's attempt to wrap numbers around something so fundamentally huge that our brains simply weren't designed to process it. We're creatures who evolved to understand the distance from our cave to the watering hole, not the distance from our solar system to the nearest star. Our neural pathways were carved by thousands of generations who never traveled faster than they could run or farther than they could walk in a few days. Yet here we are, trying to comprehend distances that would make our ancestors' minds simply shut down in self-defense. The light year represents one of the most beautiful paradoxes in science. It's simultaneously the most intuitive way to measure cosmic distances and completely impossible for us to truly grasp. Let's start with the basics, because even the definition of a light year reveals something profound about the nature of space and time. A light year is the distance that light travels in exactly 1 year. Now, that might sound simple enough, but let's unpack what that really means. Light moves at approximately 300 million meters every single second. Not almost that fast, not roughly that speed, but exactly 299,792,458 meters per second through empty space. Picture light leaving the surface of a distant star right now, this very instant. That light is racing toward us at a speed so fast it could circle the Earth more than 7 times in a single second. It travels at a velocity so immense that nothing in our everyday experience comes even remotely close. The fastest jet aircraft would seem frozen in comparison. The speediest rocket we've ever built would appear to be crawling. Now multiply that incredible speed by the number of seconds in a year. We're talking about 31,557,600 seconds, each one seeing light travel nearly 300 million meters. When you work out the mathematics, a single light year equals approximately 9.46 trillion kilometers. That's 9,460 billion kilometers for 1 light year. But here's where our brains start to rebel. We can write down the numbers, we can perform the calculations, but we cannot truly comprehend what 9.46 trillion kilometers actually means. Our minds have no framework for processing such vastness. It's like trying to count to infinity or imagine what nothing looks like. To put this in perspective, let's try some comparisons that might help. Though I warn you, they'll probably just make the incomprehensibility more obvious. If you could somehow travel at the speed of our fastest spacecraft, it would take you approximately 37,000 years to cover a single light year. Think about that for a moment. The entire recorded history of human civilization spans only about 5,000 years. You would need more than 7 complete cycles of all human history just to travel 1 light year. The space shuttle, when it was operational, traveled at roughly 28,000 kilometers per hour. At that speed, which is already far beyond anything we experience in our daily lives, it would take about 37,000 years to cover 1 light year. That's longer than modern humans have existed as a species. Our earliest cave paintings are only about 40,000 years old. The distance of a single light year represents a journey longer than the entire story of human artistic expression. But perhaps even more mind-bending is this realization. When we look up at the night sky, we're not seeing the universe as it is right now. We're seeing it as it was. Every photon of light that enters your eye has been traveling through space for years, decades, centuries, or even billions of years to reach you. You are literally looking back in time every time you gaze upward. The light from our sun, our nearest star, takes about 8 minutes to reach Earth. When you step outside on a sunny day and feel that warmth on your face, you're experiencing sunshine that left the sun's surface 8 minutes ago. If the sun suddenly vanished right now, this very instant, we wouldn't know about it for 8 minutes. We'd continue to see it, continue to feel its warmth, continue to orbit around empty space where it used to be, completely unaware that our star was gone. But the sun is practically next door compared to other stars. The nearest star beyond our sun is Proxima Centauri, part of the Alpha Centauri system, located 4.24 light-years away. That innocent little number, 4.24, represents a distance so vast that it challenges everything we think we know about travel and exploration. If we could somehow build a spacecraft capable of traveling at 1% of the speed of light, which would be an absolutely miraculous achievement, representing technology far beyond anything we can currently imagine, it would still take 424 years to reach Proxima Centauri. That's longer than the United States has existed as a nation. Christopher Columbus discovered the Americas only about 530 years ago. A journey to our nearest stellar neighbor would take nearly as long as the entire age of exploration. And Proxima Centauri is right next door on cosmic scales. It's practically in our backyard. When astronomers talk about nearby stars, they're referring to objects that are thousands of light years away. When we discuss distant galaxies, we're looking at distances measured in millions and billions of light years. Consider the Andromeda Galaxy, the nearest major galaxy to our own Milky Way. It's located about 2.5 million light years from Earth. When you look at Andromeda through a telescope, or even with the naked eye if you know where to look and have dark skies, you're seeing light that began its journey when our earliest human ancestors were just beginning to use stone tools. The light hitting your retina left Andromeda when the genus Homo was first emerging in Africa. That photon you're observing has been traveling through the emptiness of space for longer than our species has existed. It has crossed a void so vast that if you could somehow travel at the speed of light itself, the absolute speed limit of the universe, it would still take you 2.5 million years to make the journey. But here's where the story gets even more extraordinary. Andromeda is approaching us. It's moving through space toward the Milky Way at about 110 kilometers per second. In approximately 4 billion years, our two galaxies will collide and merge in a cosmic dance of unimaginable scale and beauty. Even at that tremendous speed, it will take billions of years for Andromeda to cross the space between us. Now, let's push our minds even further. The observable universe, the bubble of space around us from which light has had time to reach Earth since the Big Bang, is approximately 93 billion light-years in diameter. When we observe the most distant objects in the universe, we're seeing light that has been traveling toward us for nearly 14 billion years. We're looking at the universe when it was young, when the first stars were forming, when space itself was smaller and hotter and completely alien to anything we could recognize today. The cosmic microwave background, the faint afterglow of the Big Bang that fills all of space, represents light that has been traveling for about 13.8 billion years. When that light began its journey, there were no stars, no galaxies, no planets, no complexity of any kind. The universe was a hot, dense soup of elementary particles slowly cooling as space expanded. Yet here's the truly mind-breaking part. Those most distant objects we can observe are now much farther away than 13.8 billion light-years. Due to the expansion of space itself, objects that emitted light 13.8 billion years ago are now about 46 billion light-years away from us. The light we see tonight left those distant regions when they were much closer, but space has been stretching the entire time, carrying those objects farther and farther away, even as their ancient light continues to race toward us. This creates a fundamental paradox in our understanding. We can see objects that are now unreachably distant. Their current light will never reach us because they're receding faster than light can travel through expanding space. We're observing ghosts of the cosmic past, watching a universe that no longer exists in the form we see it. The light year forces us to confront the profound relationship between space and time. Distance and duration become intertwined in ways that challenge our basic intuitions about reality. When we measure cosmic distances in light years, we're simultaneously measuring how far back in time we're looking. Space becomes a time machine, and every telescope becomes a window into the past. But perhaps the most humbling aspect of the light year is what it reveals about our place in the cosmos. The distances between stars in our galaxy are measured in light years. The distances between galaxies are measured in millions of light years. The observable universe spans billions of light years in every direction. We exist on a planet orbiting a star in a galaxy that is itself just one of hundreds of billions of galaxies scattered across space on scales that dwarf comprehension. Our entire solar system, from the Sun to the outermost reaches of the Kuiper Belt, spans only about 0.002 light-years across. Think about that for a moment. Everything we've ever known, every planet we've studied, every asteroid we've tracked, every comet that has ever graced our skies, exists within a bubble that represents 2/1000ths of a single light year. It's like comparing a grain of sand to a football field, except even that comparison fails to capture the true scale we're dealing with. The nearest star-forming region to us, the breathtaking Orion Nebula that decorates our winter skies, lies approximately 1,300 light-years away. When you look at those stellar nurseries through a telescope, witnessing the birth of new stars in clouds of gas and dust, you're observing events that happened when the Roman Empire was at its height. The light from those newborn stars began its journey toward Earth when gladiators fought in the Colosseum and Hadrian's Wall was being constructed. Moving deeper into our galactic neighborhood, the center of our own Milky Way galaxy sits roughly 27,000 light-years from our solar system. The supermassive black hole that anchors our galaxy, that invisible monster around which hundreds of billions of stars orbit in their cosmic dance, is separated from us by a distance that light takes 27,000 years to cross. When the light we see from the galactic center began its journey, our species was still learning to make cave paintings in Europe. These numbers start to feel abstract, don't they? Our minds begin to glaze over when confronted with such vastness. It's a defense mechanism, really. Our brains simply weren't built to process information on these scales. We evolved to understand the distance from tree to tree, from valley to mountain, from village to village. Cosmic distances exist in a realm completely outside our evolutionary experience. Let me try a different approach. Imagine you could shrink the entire universe down to a more manageable size. Let's say we scale everything so that our solar system becomes the size of a coin, about 2 centimeters across. At this scale, Proxima Centauri, our nearest stellar neighbor, would be located about 1,100 kilometers away. That's roughly the distance from London to Rome, or from New York to Jacksonville. Even our closest star would require a significant journey across multiple countries. But we're just getting started with this scaling exercise. The center of our galaxy would be approximately 5.5 million kilometers away at this scale. That's more than 14 times the distance from Earth to the Moon. The Andromeda Galaxy would be positioned about 50 million kilometers away, roughly 1/3 of the distance from Earth to the Sun. And the edge of the observable universe, it would extend about 950 million kilometers in every direction, placing it beyond the orbit of Jupiter. Even when we shrink the entire cosmos down to planetary scales, the distances remain almost incomprehensibly vast. This is the tyranny of the light year. No matter how we try to visualize it, no matter what analogies we construct, it stubbornly refuses to fit into our human-sized understanding of distance. Here's another way to think about it. Light travels so fast that it can circle the Earth's equator more than 7 times in a single second. In 1 year, light covers a distance so immense that if you could lay a trail of pennies from here to the nearest star, you would need approximately 3 trillion pennies. That's more pennies than there are atoms in a human body. The trail would weigh more than all the copper ever mined in human history, multiplied by billions. The psychological impact of contemplating these distances cannot be overstated. There's something deeply unsettling about realizing that we are isolated on our tiny world by gulfs of emptiness so vast that they challenge the very concept of connection. The space between stars isn't just empty, it's monumentally, crushingly, overwhelmingly empty. If you could somehow survive the journey and travel at the speed of light toward Proxima Centauri, you would spend over 4 years crossing absolutely nothing but vacuum, with no landmarks, no reference points, no indication that you were making progress except for the slowly changing positions of distant stars. This emptiness between the stars represents one of the most profound aspects of cosmic architecture. Space is not filled with stuff the way our earthly environment is filled with air, trees, buildings, and landscape. Interstellar space is mostly nothing, punctuated by incredibly rare encounters with the occasional hydrogen atom. If you could take a cube of interstellar space the size of a refrigerator, it would contain, on average, fewer atoms than you exhale in a single breath. Yet within this vast emptiness, extraordinary things are happening. Stellar winds carry charged particles across light years of space. Magnetic fields stretch between star systems, invisible highways along which cosmic rays race at nearly the speed of light. Gravitational waves ripple through the fabric of space-time itself, carrying information about colliding black holes and neutron stars from distances measured in billions of light years. The light year also reveals something profound about the nature of information itself. Every photon that reaches us from distant stars is a messenger carrying encoded information about its place of origin. The color of starlight tells us about stellar temperature. The pattern of absorption lines reveals elemental composition. The subtle dimming and brightening can indicate the presence of orbiting planets. The polarization carries clues about magnetic fields and dust clouds. But these photons are ancient historians, reporting on conditions that existed years, centuries, or millennia ago. When we analyze the spectrum of light from a star 100 light-years away, we're conducting archaeology, studying the chemical composition and physical conditions that existed a century in the past. We're seeing that star as it was when our great-grandparents were children, completely unaware of what might have happened to it in the intervening decades. This temporal displacement creates fascinating paradoxes. It's entirely possible that some of the stars we see in our night sky have already died, their light continuing to race toward us across the cosmic dark like messages from the grave. Conversely, new stars may have been born in regions where we still see only empty space, their first light still years or decades away from reaching our telescopes. The concept of simultaneity becomes meaningless on cosmic scales. When we say something is happening now in the Andromeda galaxy, we're making a statement that has no physical meaning. There is no cosmic now that extends across space. Events that appear simultaneous to us may have actually occurred millions of years apart. The universe doesn't have a universal clock ticking away the same moments everywhere at once. This relativity of time and distance challenges our most basic assumptions about cause and effect. We're accustomed to thinking in terms of linear causation, where events unfold in a clear sequence of before and after. But on cosmic scales, the light year reveals that causation itself becomes twisted by distance. An explosion in a distant galaxy may influence conditions in intergalactic space for millions of years, creating effects that propagate outward at the speed of light, reaching different locations at different times. The measurement of cosmic distances in light years also highlights one of the most remarkable achievements of human intellect. Despite being creatures bound to a single small world, despite having brains that evolved to navigate terrestrial environments, we have somehow managed to develop tools and techniques that allow us to measure distances across the universe with extraordinary precision. We use parallax, the apparent shift in stellar positions as Earth orbits the Sun to measure distances to nearby stars. We employ standard candles, objects of known brightness, to gauge distances to remote galaxies. We analyze the redshift of light, the stretching of wavelengths caused by cosmic expansion, to peer back toward the very beginning of time itself. Each of these techniques represents a triumph of human creativity and persistence. Ancient astronomers noticed that some stars appeared to move slightly against the background of more distant stars as the seasons changed. Through careful observation and mathematical analysis, they realized they were seeing the same effect that makes nearby objects appear to shift position when you close one eye and then the other. By measuring these tiny angular shifts and combining them with knowledge of Earth's orbital diameter, astronomers could calculate distances to stars using nothing more than geometry and patience. The story of distance measurement in astronomy reads like an epic saga of human curiosity, pushing against the boundaries of the knowable. Each breakthrough opened new vistas of understanding, while simultaneously revealing how much more there was to discover. The light year emerged from this tradition as both a practical tool and a conceptual bridge between human experience and cosmic reality. But perhaps the most profound lesson of the light year is what it teaches us about perspective and humility. When we truly contemplate the distances between stars, when we allow ourselves to feel the full weight of cosmic emptiness, something fundamental shifts in our understanding of our place in existence. We begin to see our daily concerns, our political divisions, our temporary worries in the context of a universe so vast and ancient that our entire species represents barely a whisper in the cosmic conversation. Yet this humbling realization doesn't diminish us. Instead, it reveals something extraordinary about the human spirit. Despite our cosmic insignificance, despite being temporary arrangements of atoms on a small world orbiting an ordinary star in an unremarkable galaxy, we have somehow developed the capacity to contemplate infinity itself. We can measure the unmeasurable, conceive of the inconceivable, and find meaning in scales that dwarf comprehension. The light year stands as a monument to this remarkable capacity. It represents our refusal to be limited by the boundaries of our direct experience. We may never travel to the stars, may never cross the light years that separate us from our cosmic neighbors, but we can measure those distances, study the objects they contain, and incorporate their reality into our understanding of existence. In the gentle darkness of space, light continues its ancient journey from star to star, galaxy to galaxy, carrying information across distances that challenge everything we think we know about space and time. Every photon that enters our telescopes tonight has crossed gulfs of emptiness so vast they break our brains. Yet somehow, impossibly, we have learned to read their stories and incorporate their messages into our growing understanding of the cosmos we call home. The more we contemplate these cosmic distances, the more we encounter a peculiar phenomenon that affects every human who has ever tried to truly grasp the scale of the universe. Our minds begin to play tricks on us. We start to experience what psychologists call cognitive saturation, a state where our brains simply stop processing new information about scale because they've reached the absolute limit of what they can meaningfully comprehend. It's like trying to count to 1 trillion. You can say the words, you can write down the numbers, but at some point your mind just gives up trying to attach any real meaning to what those numbers represent. the light year pushes us past that breaking point almost immediately. We can understand that 1 light year equals 9.46 trillion kilometers. But what does 9.46 trillion actually mean to a species that has trouble truly comprehending even a million? Let me share something that might help illustrate just how profoundly these distances exceed our cognitive capabilities. If you started counting right now, 1 number per second, without stopping to eat, sleep, or rest, it would take you about 12 days to count to a million. That seems manageable, doesn't it? Now, to count to a billion at the same rate would require 32 years of continuous counting. And to count to a trillion, that would take approximately 32,000 years of non-stop counting. Remember, we're talking about 9.46 trillion kilometers for just 1 light year. The numbers become so abstract that they lose all connection to anything we might call intuitive understanding. Our brains evolved to track perhaps a dozen objects at once, to estimate distances measured in meters or kilometers, to plan ahead for seasons rather than millennia. We're asking these same neural networks to process distances that dwarf not just our planet, but our entire solar system. There's a beautiful irony here. The light year was invented to make cosmic distances more comprehensible, yet it simultaneously reveals just how incomprehensible they truly are. It's like creating a new word to describe silence and discovering that the word itself is too quiet to hear. The light year gives us a tool to measure the unmeasurable, while constantly reminding us that what we're measuring exists in a realm completely beyond our experiential reality. Consider this fascinating aspect of light years that most people never contemplate. When astronomers discover a new exoplanet orbiting a star 50 light years away, they're not just finding a distant world. They're discovering a planet as it existed 50 years ago. If that planet harbored life, if civilizations rose and fell on its surface, if entire ecosystems evolved and went extinct, we would be completely unaware of any changes that occurred in the past 50 years. This temporal displacement creates a kind of cosmic archaeology, where distance and time become indistinguishable. Every telescope becomes a time machine, every observation a glimpse into the past. The farther we look into space, the deeper we peer into history. The most distant galaxies we can observe appear as they were when the universe was young, when the first stars were igniting in the cosmic dawn, when the very chemistry of space was fundamentally different from what we observe nearby. But here's where the light year reveals something even more profound about the nature of reality itself. These vast distances don't just separate us from distant objects in space. They separate us from different epochs of cosmic time. When we look at the Andromeda galaxy, we're seeing it as it appeared 2.5 million years ago. When we observe more distant galaxies, we're witnessing them as they existed when our sun was forming, when life on Earth was just beginning, when the universe itself was younger and smaller and stranger. This means that our view of the cosmos is fundamentally historical. We never see the universe as it is now. We only see it as it was, layer upon layer of ancient light, creating a kind of temporal archaeology written across the sky. The nearest stars show us the recent past, while the most distant galaxies reveal the ancient past. There is no present moment that extends across the universe. There is only an ever-expanding sphere of causality, growing outward at the speed of light, carrying information about what was rather than what is. The psychological impact of contemplating these realities can be overwhelming. We're confronted with the fact that we exist in a kind of cosmic isolation, separated from the rest of the universe not just by distance, but by time itself. The light reaching us tonight from distant stars began its journey before human civilization existed. The photons entering our eyes have crossed gulfs of space so vast that entire species could evolve and go extinct during their transit. Yet there's something deeply beautiful about this isolation. Every photon that reaches Earth has chosen our tiny world as its destination after crossing unimaginable distances. The light from a star 1,000 light years away has traveled for a millennium through the emptiness of space to arrive at this precise moment and enter your retina. In a universe of infinite possible destinations, that ancient light found its way to you. This realization transforms our relationship with starlight. When you step outside on a clear night and look up at the stellar tapestry above, you're not just seeing distant suns. You're witnessing the culmination of countless individual journeys that began years, decades, centuries, or millennia ago. Each point of light represents a photon that has crossed the cosmic dark to deliver its message directly to your eyes. The light year also reveals something extraordinary about the nature of space itself. The emptiness between stars isn't just empty space as we might imagine it. It's a dynamic medium filled with invisible activity. Magnetic fields stretch across light years, creating invisible highways along which charged particles race at tremendous speeds. Gravitational waves ripple through space-time, carrying information about distant cosmic catastrophes. The quantum vacuum itself buzzes with virtual particles popping in and out of existence. This isn't the static emptiness we might imagine when we think of vacant space. It's a living, breathing medium through which light propagates, carrying information across distances so vast they challenge comprehension. The photon that left a distant star a century ago has navigated through this complex environment, dodging cosmic dust, riding gravitational currents, maintaining its trajectory across light years of space to reach us with its message intact. But perhaps the most mind-bending aspect of the light year is how it reveals the fundamental weirdness of cosmic expansion. The most distant objects we can observe are now much farther away than the distance their light has traveled to reach us. A galaxy whose light has been traveling for 10 billion years to reach us is now approximately 24 billion light years away due to the expansion of space itself. This creates a strange situation where we can see objects that are now unreachably distant. Their current light will never reach us because they're receding faster than light can travel through expanding space. We're observing ghosts of the cosmic past, watching a universe that no longer exists in the form we see it. The expansion of space means that the cosmic horizon is constantly shrinking. Every day, more of the universe slips beyond our ability to observe, disappearing forever behind an expanding veil of space-time. The light year forces us to confront these paradoxes of cosmic observation. Distance becomes time, observation becomes archaeology, and the present moment dissolves into a collection of ancient images from different epochs of cosmic history. We're not just looking at space when we gaze upward. We're looking through time itself, witnessing the universe as it unfolded across billions of years of cosmic evolution. These realizations have profound implications for how we understand our place in existence. We're not just small in space. We're brief in time. The light reaching us tonight from distant galaxies began its journey when the universe was young, when the chemistry of space was different, when the very structure of cosmic evolution was unfolding in ways we can barely comprehend. Yet somehow, impossibly, we've learned to read these ancient messages. We can decode the information carried by photons that have traveled for billions of years to reach us. We can determine the temperature, composition, motion, and history of objects so distant that their light began its journey before our solar system existed. We can peer back toward the very beginning of time itself and observe the afterglow of creation. This represents one of the most remarkable achievements in the history of human thought. Despite being creatures confined to a single small world, despite having lifespans measured in decades rather than cosmic ages, we have somehow learned to observe and understand phenomena occurring on scales that dwarf our comprehension. The light year stands as both a measure of our cosmic insignificance and a monument to the power of human curiosity to transcend the boundaries of direct experience. Through all of this cosmic contemplation, there's an aspect of light years that strikes me as particularly haunting. It's the realization that we live in a universe where true simultaneity is impossible. When we say that something is happening right now on a planet orbiting Proxima Centauri, we're making a statement that has no physical meaning. There is no universal now that connects us to that distant world. Events that we might imagine are occurring simultaneously are actually separated by the fundamental speed limit of information itself. This breakdown of simultaneity on cosmic scales reveals something profound about the nature of reality. We're accustomed to living in a world where cause and effect unfold in clear, immediate sequences. You flip a switch, the light turns on. You speak, someone hears you. You wave at a friend across the street, they wave back. These interactions feel instantaneous because they occur over distances so small that light travel time is negligible. But stretch those distances to light years, and the comfortable illusion of simultaneous existence dissolves completely. If you could somehow send a message to an alien civilization on a planet 10 light years away, your greeting would take 10 years to arrive. Their response would take another 10 years to return. A simple conversation would span decades. You might grow old and die waiting for the reply to a question you asked as a young person. This temporal isolation creates a profound loneliness that permeates cosmic distances. Every star system exists in its own bubble of causality, connected to the rest of the universe only by ancient light and the slow propagation of gravitational influences. The Milky Way itself is like a collection of isolated islands, each separated from its neighbors by gulfs of space and time that dwarf human comprehension. Yet there's something deeply moving about the fact that these islands of matter and energy continue to communicate across such impossible distances. Stars pour their light into the cosmic void with no guarantee that anyone will ever receive their messages. Galaxies broadcast their radio waves into emptiness that may never encounter another listening ear. The universe is filled with conversations that span millions of years, dialogues conducted at the speed of light across distances that break our brains. Consider the extraordinary patience required for cosmic communication. The Andromeda Galaxy has been sending us its light for 2.5 million years. Every photon that reaches us tonight represents a tiny piece of information about conditions in that distant spiral of stars as they existed when our earliest ancestors were just beginning to walk upright. The galaxy has been broadcasting continuously across the eons, never knowing if anyone would be here to receive its transmission. And we almost weren't. For most of the time that Andromeda's light has been traveling toward Earth, there was no one here capable of understanding what they were seeing. The photons arrived faithfully, as they had for millions of years, but they fell on worlds populated by creatures who saw them simply as mysterious lights in the sky. Only in the last few centuries have we developed the tools and understanding necessary to decode the messages hidden in that ancient starlight. This raises a fascinating question that touches the very heart of cosmic communication. How many other signals are reaching us right now that we simply don't know how to interpret? How many messages are hidden in the light years of space around us, waiting for minds capable of understanding their meaning? The universe may be far more talkative than we realize, conducting conversations in languages we haven't yet learned to speak. The light year also reveals something extraordinary about the persistence of information. Once a photon begins its journey through space, it carries its message with almost infinite patience. It doesn't degrade or decay as it travels. It doesn't forget what it's trying to communicate. A photon that left a star 1 billion years ago carries exactly the same information today as it did when it began its journey. The light reaching us from the most distant galaxies is as fresh and informative as the day it was emitted, despite having traveled across most of the observable universe to reach us. This permanence of cosmic information creates a kind of universal library written in light. Every star that has ever shone has sent its autobiography racing outward into space. Every galaxy has broadcast its history across the cosmos. Every cosmic event, from supernovas to the formation of planetary systems, has encoded its story in electromagnetic radiation that continues to propagate through space long after the events themselves have concluded. We're surrounded by this library of light, immersed in information that has been accumulating for billions of years. The challenge isn't finding the messages, it's learning how to read them. Every advancement in astronomy represents a new chapter in our growing literacy with cosmic communication. We've learned to decode temperature from stellar color, to infer chemical composition from spectral lines, to deduce motion from Doppler shifts. We're slowly becoming fluent in the language that the universe has been speaking since the first stars ignited. But here's what truly breaks our brains about light years. The scale of cosmic communication is so vast that individual human lives become almost meaningless in the context of these interstellar conversations. A signal sent from Earth to Alpha Centauri and back would take more than 8 years to complete the round trip. That's longer than many people spend in school, longer than most romantic relationships last, long enough for children to grow into teenagers. Imagine trying to maintain a friendship across such distances. You send a message when you're 20 years old, full of hopes and dreams and plans for the future. The reply arrives when you're nearly 30, possibly married with children, having lived through experiences that have fundamentally changed who you are. The person who receives your friend's response is literally a different human being than the one who sent the original message. Identity itself becomes fluid across light-year distances. This temporal stretching of human experience across cosmic scales reveals something profound about the relationship between consciousness and space. Our minds operate on timescales measured in milliseconds to decades. Our thoughts unfold over seconds, our conversations over minutes, our relationships over years. But the universe conducts its business on timescales measured in millions and billions of years. The formation of a star system takes longer than complex life has existed on Earth. The evolution of a galaxy spans timeframes that dwarf the entire history of multicellular organisms. We exist in a narrow slice of cosmic time, a brief window of awareness in a universe that has been unfolding for nearly 14 billion years. The light reaching us tonight from distant stars began its journey when the universe was fundamentally different. Some of that light left its source when there were no planets, no complex chemistry, no possibility of life as we understand it. We're receiving messages from an alien cosmos, a universe so different from our current reality that it might as well be a completely foreign dimension. Yet somehow, miraculously, we've learned to read these ancient messages and piece together the story of cosmic evolution. We can trace the universe from its hot, dense beginning through the formation of the first atoms, the ignition of the first stars, the assembly of galaxies, and the emergence of the complex chemistry that eventually gave rise to planets like Earth. We're cosmic archaeologists, using light years as our excavation tool, digging deeper into space to uncover ever more ancient epochs of universal history. The light year serves as both a measuring stick and a time machine, allowing us to observe directly the processes that shape the cosmos we inhabit. When we look at a star-forming region 1,000 light years away, we're not just seeing distant stellar nurseries. We're witnessing the same processes that gave birth to our own sun 1 billion years ago. When we observe galaxies billions of light years distant, we're seeing the universe as it existed when it was young, when the basic architecture of cosmic structure was first taking shape. This direct observation of cosmic history represents something unprecedented in the story of human understanding. We're the first species on Earth, possibly the first species anywhere, to develop the capability to observe our own cosmic origins. We can see the universe as it was when the first stars were forming. We can observe the chemical evolution that created the elements necessary for planets and life. We can witness the grand narrative of cosmic evolution unfolding across space and time. But the more we observe, the more we realize how much we don't know. Every light year we peer deeper into space reveals new mysteries, new questions, new aspects of cosmic evolution that challenge our understanding. We've discovered that most of the universe consists of dark matter and dark energy, substances we can barely detect and don't understand at all. We've found that the expansion of space is accelerating, driven by forces that remain completely mysterious. The light year has become our guide into this cosmic mystery. It measures not just distance, but ignorance. Every light year represents a volume of space filled with phenomena we're only beginning to comprehend. The farther we look, the stranger the universe becomes. We've found galaxies that shouldn't exist, stars that are older than our current understanding suggests should be possible, and cosmic structures on scales that challenge our theories of how the universe evolved. These discoveries remind us that despite our remarkable progress in understanding cosmic distances and the messages carried by ancient light, we're still at the very beginning of our journey toward comprehending the universe we inhabit. The light year has opened doors to cosmic understanding that we never knew existed. But beyond each door, we find corridors leading to ever deeper mysteries. Perhaps that's the most beautiful aspect of contemplating light years. They remind us that no matter how much we learn, no matter how sophisticated our instruments become, the universe will always remain larger than our understanding. There will always be more light years to explore, more ancient messages to decode, more cosmic conversations to join. We're participants in a dialogue that began with the first stars and will continue long after our species has vanished from the cosmic stage. The light year doesn't just measure distance, it measures wonder itself. Every additional light year we can observe expands our capacity for awe, stretches our imagination, and reminds us that we live in a universe far more magnificent and mysterious than our earthbound experience could ever suggest. We may never travel to the stars, may never cross the light years that separate us from our cosmic neighbors, but through the patient accumulation of ancient light, we can visit them in spirit, learning their stories and incorporating their realities into our growing understanding of the infinite cosmos we call home. In this gentle contemplation of cosmic distances, we find ourselves confronting not just the scale of space, but the nature of existence itself. The light year reveals that we live in a universe where information travels at a finite speed, where distance and time become indistinguishable, where the very concept of simultaneity breaks down across cosmic scales. These aren't just abstract physics concepts. They're fundamental features of reality that shape everything from the structure of galaxies to the possibility of cosmic communication. As we drift deeper into this exploration of light years and the distances that break our brains, we begin to see that these measurements aren't just numbers on a page. They're windows into the deepest truths about the universe we inhabit. Revelations about the nature of space and time that challenge everything we thought we knew about existence itself. The more we contemplate these cosmic distances, the more we encounter something that physicists call the horizon problem, though it applies far beyond the realm of professional astronomy. It's the realization that there are fundamental limits to what we can ever know about the universe, limits imposed not by the inadequacy of our instruments, but by the very structure of space-time itself. Picture this scenario that perfectly illustrates how light years create boundaries around knowledge itself. Imagine two civilizations exist on planets orbiting stars that are each 50 light years from Earth, but located in opposite directions. From our perspective here on our pale blue dot, these two worlds appear to exist simultaneously in our present moment. We can observe both through our telescopes on the same night, under the same sky, seemingly sharing the same cosmic instant. But here's where the light year reveals the profound strangeness of cosmic reality. Those two civilizations, despite appearing simultaneous to us, are actually separated by a temporal gulf of 100 years. If something significant happened on the first world exactly when we observe it, that information would take 50 years to reach us, and then another 100 years to travel from us to the second world. The two civilizations exist in completely disconnected bubbles of causality, unable to influence each other for a minimum of 100 years, even if they could somehow communicate at the speed of light. This creates islands of existence throughout the cosmos, each separated from its neighbors by motes of time measured in light years. Every star system exists in its own temporal bubble, connected to the rest of the universe only through the patient propagation of light and gravitational influences. The galaxy becomes a collection of isolated moments, each unfolding at its own pace, each unaware of the current state of its neighbors. Now let's push this concept to its ultimate extreme and contemplate what happens when we consider the edge of the observable universe itself. The most distant galaxies we can observe appear to us as they existed roughly 13.8 billion years ago, when they were much closer to us and the universe was much smaller and denser. But due to cosmic expansion, those same galaxies are now approximately 46 billion light-years away from us. Here's what breaks our brains completely. Those distant galaxies have continued to evolve, to change, to potentially harbor entirely different cosmic phenomena than what we observe. Stars have been born and died. Planets may have formed and developed complex chemistry. Entire civilizations might have risen and fallen, and we will never know about any of it. The light carrying information about these more recent events is racing toward us across expanding space. But space itself is stretching faster than the light can travel. This means that there are events happening right now in those distant regions that we are fundamentally prohibited from ever observing. Not because our telescopes aren't powerful enough, not because we haven't developed the right technology, but because the very structure of space-time makes that information permanently inaccessible. We live inside an observational cage created by the speed of light and the expansion of space, forever limited in what we can know about our cosmic neighbors. But the story becomes even stranger when we consider cosmic expansion itself. Edwin Hubble's discovery that distant galaxies are receding from us revealed something that initially seemed impossible. The farther away a galaxy is, the faster it appears to be moving away from us. At first glance, this might suggest that we're at the center of the universe, with everything rushing away from our special location. But the light year helps us understand why this apparent cosmic fleeing is actually evidence of something far more profound. Space itself is expanding uniformly in all directions. Imagine a balloon with dots marked on its surface. As you inflate the balloon, every dot moves away from every other dot, with the most distant dots appearing to recede fastest from any particular reference point. The dots aren't actually moving through the balloon's surface. Rather, the surface itself is stretching, carrying the dots along with it. Now scale this up to cosmic proportions. Galaxies aren't flying through space away from us. Space itself is expanding between us and them, carrying distant galaxies along like boats on a rising tide. This expansion means that the most distant galaxies are receding from us at speeds that exceed the velocity of light itself. Not because they're moving through space faster than light, which would violate the fundamental laws of physics, but because space itself is expanding at rates that dwarf even the ultimate cosmic speed limit. This creates a phenomenon that sounds like science fiction, but represents the actual structure of our universe. There are galaxies out there whose light began its journey toward us billions of years ago, but due to cosmic expansion, that light will never reach us. The space between us and those distant beacons is stretching faster than their photons can cross it. They exist in a realm forever beyond our observational horizon, permanently disconnected from our ability to study or understand them. Think about the implications of this cosmic isolation. There are potentially trillions of galaxies, each containing hundreds of billions of stars, each star possibly surrounded by planets, each planet potentially harboring phenomena we can't even imagine, and all of it exists in a region of space that is fundamentally unreachable by any information or influence from our cosmic neighborhood. The light year reveals that we don't just live in a large universe. We live in a universe with a specific and limited size, bounded not by walls or barriers, but by the interplay between the speed of light and the expansion of space itself. Our observable universe forms a sphere approximately 93 billion light-years in diameter, beyond which lies the unknowable cosmic beyond. But here's where the concept becomes truly mind-bending. That observable sphere is constantly changing. Every second, light from slightly more distant regions reaches us for the first time, expanding our cosmic horizon by roughly 300,000 kilometers. Meanwhile, due to cosmic expansion, other regions that we can currently observe are slowly slipping beyond our future ability to see them. The universe is simultaneously revealing new secrets while hiding others forever. This dynamic boundary creates a strange temporal paradox. We can currently observe galaxies that are receding so rapidly they will eventually disappear from view entirely. Future astronomers, billions of years from now, will inhabit a much lonelier cosmos where the evidence for cosmic expansion, the Big Bang, and the true scale of the universe has been stretched beyond detection. They'll look out at a sky containing only the local group of galaxies, completely unaware of the vast cosmic web that we're privileged to observe today. The light year forces us to confront this cosmic loneliness in the most visceral way possible. Every photon that reaches us tonight has crossed distances so vast that entire civilizations could rise and fall during its journey. The light from distant quasars began its voyage when the universe was young and chaotic, when galaxies were still forming through violent mergers, when the chemistry of space was fundamentally different from what we observe in our cosmic neighborhood. These ancient photons carry within them information about epochs of cosmic evolution that no longer exist anywhere in the universe. They're time capsules from a cosmos that has evolved beyond recognition. Messages from a universe that was stranger and more violent than anything we observe today. When we capture this ancient light in our telescopes, we're not just observing distant objects. We're witnessing the universe's autobiography, written in electromagnetic radiation across the vast libraries of space. Consider the profound patience required for this cosmic communication. A photon that reaches us tonight from a galaxy 10 billion light-years away began its journey when our solar system was still forming from a disk of dust and gas around the young sun. That photon has traveled through the expanding cosmos for more than twice as long as complex life has existed on Earth. It has crossed distances so vast that if you could somehow trace its path backward, you would journey through regions of space that no longer exist in the form they had when the photon passed through them. During its billion-year journey, that single photon has witnessed the universe evolve around it. It has passed through intergalactic space as that space expanded and cooled. It has traveled through regions where new galaxies formed and old ones merged. It has crossed vast cosmic voids and navigated the filaments of the cosmic web. All the while, it has maintained perfect fidelity to its original message, carrying information about conditions that existed when the universe was fundamentally different from the cosmos we observe today. This temporal archaeology extends to every aspect of cosmic observation. When we study the cosmic microwave background radiation, we're observing light that has been traveling for nearly 13.8 billion years. This radiation represents the oldest light in the universe, emitted when the cosmos first became transparent to electromagnetic radiation. It carries within it information about the universe when it was only 380,000 years old, when space was filled with a hot plasma of protons and electrons slowly cooling as expansion continued. The patterns we observe in this ancient light reveal the tiny density fluctuations that would eventually grow into the large-scale structure of the universe we see today. Every galaxy, every cluster of galaxies, every vast cosmic void can trace its origins back to these primordial variations in the cosmic microwave background. We're literally observing the seeds from which all cosmic structure grew, preserved in light that has been traveling since the dawn of transparency itself. But the light year also reveals something deeply unsettling about the nature of cosmic observation. We can never observe the universe as it actually exists in this moment. We can only observe it as it was, layer upon layer of ancient light, creating a kind of temporal archaeology written across the sky. The nearest stars show us the recent past, while the most distant galaxies reveal the ancient past. There is no present moment that extends across the cosmos. This means that our entire understanding of the universe is fundamentally historical. Every photograph taken by the Hubble Space Telescope or the James Webb Space Telescope is a historical document showing us cosmic conditions that existed years, centuries, millennia, or billions of years ago. We're cosmic historians, piecing together the story of universal evolution from messages sent across the light years by objects that may no longer exist in the forms we observe. The psychological impact of truly contemplating this temporal isolation can be overwhelming. We're confronted with the realization that we exist in a kind of cosmic solitude, forever separated from the rest of the universe by barriers of space and time that dwarf human comprehension. The light reaching us from distant stars began its journey before human civilization existed. The photons entering our eyes tonight have crossed gulfs of emptiness so vast that entire species could evolve and go extinct during their transit. Yet there's something profoundly beautiful about this cosmic message system. Every star that has ever shone has sent its story racing outward into space. Every galaxy has broadcast its history across the cosmos. Every cosmic event, from supernovae to the formation of planetary systems, has encoded its narrative in electromagnetic radiation that continues to propagate through space long after the events themselves have concluded. We're immersed in this constant rain of information from across the universe. Ancient light streams down upon us from every direction, carrying news from cosmic epochs that span the entire history of the universe. The challenge isn't finding these messages, it's learning how to read them. Every advancement in astronomy represents a new breakthrough in our growing literacy with cosmic communication. The light year also reveals something extraordinary about the persistence and fragility of cosmic information. A photon can travel for billions of years across the expanding universe without losing its message, maintaining perfect fidelity to the information it carries about its place and time of origin. Yet this same information can be completely lost if it encounters even a single dust grain during its cosmic journey, or if it arrives at a location where no one is equipped to receive and interpret its message. This creates a poignant irony in cosmic communication. The universe is constantly broadcasting its history and current state across the light years, sending out signals that carry information about stellar temperatures, chemical compositions, galactic motions, and the fundamental processes that govern cosmic evolution. But for most of the universe's 13.8 billion year history, there was no one listening. The signals arrived faithfully, as they had for eons, but they fell on worlds without the consciousness or technology necessary to decode their meaning. We've only recently joined this cosmic conversation. For the vast majority of the time that ancient starlight has been traveling toward Earth, there were no minds here capable of understanding what they were observing. Only in the last few centuries have we developed the tools and understanding necessary to begin reading the messages hidden in light that has crossed the light years to reach us. This raises profound questions about cosmic communication and consciousness. How many other signals are reaching us right now that we simply don't know how to interpret? How many layers of information are hidden in the light years of space around us, waiting for minds capable of understanding their deeper meaning? The universe may be far more communicative than we realize, conducting conversations in languages we haven't yet learned to speak. The concept of the light year also forces us to confront the relationship between knowledge and mortality. Individual human lifespans are measured in decades, while cosmic processes unfold over millions and billions of years. We can observe stellar evolution, but only as snapshots frozen in ancient light. We can witness the formation of galaxies, but only by looking at different galaxies in various stages of development, like studying human growth by observing many different people of different ages at a single moment. This temporal mismatch between human consciousness and cosmic evolution creates a unique form of scientific investigation. We're detectives studying a crime scene that spans billions of years, piecing together evidence from light years of space to reconstruct events that unfolded over time frames that dwarf the entire history of complex life on Earth. We're archaeologists of infinity, using photons as our artifacts, measuring distance in time and time in distance. The more we study these cosmic distances, the more we realize that the light year isn't just a unit of measurement. It's a fundamental feature of reality that shapes everything from the structure of space-time to the possibility of knowledge itself. It represents the speed at which cause and effect propagate through the universe, the rate at which information travels, the pace at which reality updates itself from moment to moment. Every interaction in the cosmos, from the collision of galaxies to the formation of planets, is governed by this ultimate speed limit. Nothing can happen instantaneously across cosmic distances. Everything must respect the light-year barrier, the fundamental constraint that information cannot travel faster than light can carry it. This creates a universe where events unfold at different rates in different locations, where simultaneity becomes meaningless across vast distances, where the very concept of now dissolves into a collection of ancient images from different epochs of cosmic time. As we continue our journey through these mind-breaking distances, we find ourselves confronting not just the scale of the universe, but the fundamental nature of existence itself. The light year reveals that we live in a cosmos where space and time are woven together in ways that challenge our most basic intuitions about reality. Distance becomes duration, observation becomes archaeology, and the present moment dissolves into layers of ancient light, carrying messages from across the vast reaches of space and time. In contemplating these cosmic distances, we're not just measuring space, we're exploring the very architecture of reality, discovering the rules that govern how information flows through the universe, how causality propagates across the cosmic web, and how consciousness itself relates to the infinite expanses of space and time that surround us. The light year serves as our guide into these deepest mysteries, measuring not just the distances between stars, but the gaps in our understanding of the cosmos we call home. Home. The relationship between light years and human comprehension becomes even more twisted when we consider what happens to our sense of identity across these cosmic distances. Imagine trying to maintain a coherent sense of self while communicating with someone on a planet orbiting Proxima Centauri. You send a message when you're 25 years old, perhaps sharing your hopes for the future, your philosophical beliefs, your plans for life. That message races through space at light speed for over 4 years before reaching its destination. If your distant correspondent immediately sends a reply, it won't reach you until you're 33 years old. The person who receives their response has lived through nearly a decade of experiences, relationships, failures, and revelations that have fundamentally altered who they are. You might have children by then, or have lost loved ones, or discovered new passions that completely reshape your worldview. The young adult who sent the original message is essentially a different person than the one reading the reply. This temporal stretching of consciousness across light-year distances reveals something profound about the nature of identity itself. We think of ourselves as continuous beings, maintaining coherent personalities across time. But cosmic communication forces us to confront how much we change over periods shorter than interstellar message delays. Your past self, who initiated that conversation, becomes almost like a stranger, someone whose thoughts and concerns feel distant and perhaps even naive from your current perspective. Scale this up to civilizational timescales, and the concept becomes even more bewildering. If Earth somehow detected a signal from an alien civilization 100 light-years away, the message we received would represent their culture, technology, and knowledge from a century ago. Our reply would take another century to reach them, meaning any meaningful dialogue would span multiple human generations. The civilization that eventually receives our response might have evolved beyond recognition from the one that sent the original signal. Entire species could rise and fall during such conversations. Technological revolutions could transform societies completely. What began as a message between two civilizations might end up being received by their distant descendants, or by entirely different species that had inherited the communication infrastructure. The light year creates temporal chasms between cosmic neighbors that dwarf the entire history of human technological development. But here's where the light year reveals something even more disorienting about cosmic perspective. When we observe distant galaxies through our most powerful telescopes, we're not just seeing them as they were in the past. We're seeing them as they appeared from our current spatial location, but they were much closer to us when that light was emitted. The expansion of space means that a galaxy we observe as it appeared 10 billion years ago was actually only about 4 billion light years away when that light began its journey to us. This creates a strange situation where distance and time become completely intertwined in ways that defy intuitive understanding. The farther we look into space, the deeper we peer into time, but we're also looking at objects that were once much closer to us than they appear. It's like watching a movie of someone walking away from you, except the person in the movie was actually much closer when the filming began, and they've been moving away the entire time you've been watching. The cosmic expansion that stretches these distances also stretches the light itself, shifting its color toward the red end of the spectrum. This redshift becomes so extreme for the most distant galaxies that their visible light is stretched all the way into infrared wavelengths by the time it reaches us. We need specialized instruments to detect this ancient light that has been traveling through expanding space for most of the universe's history. Some of the most distant galaxies we can observe appear as they existed when the universe was less than 1 billion years old, when the first generation of stars was still forming from primordial hydrogen and helium. These ancient stellar nurseries were fundamentally different from anything we observe in our local cosmic neighborhood. They contained no heavy elements, no carbon or oxygen or iron, because these elements hadn't yet been forged in stellar cores and scattered by supernovae. The light from these primordial galaxies carries information about a cosmos so alien that it challenges our understanding of how stellar formation and galactic evolution actually work. We're observing chemistry and physics that no longer exists anywhere in the current universe. The processes we witness in this ancient light created the foundation for everything that came afterward, including the heavy elements that eventually made planets and life possible. This temporal archaeology becomes even more mind-bending when we consider that we can actually observe the universe becoming more chemically complex over cosmic time. By looking at galaxies at different distances, we're seeing them at different stages of cosmic evolution. Nearby galaxies show us the mature universe, rich with heavy elements and complex chemistry. More distant galaxies reveal earlier epochs when the cosmos was simpler and stranger. We can literally watch the universe learning how to make complexity. We can observe the first stars forming from pure hydrogen and helium, then see how their deaths enriched space with heavier elements that enabled the formation of more complex stellar populations. We can witness the gradual assembly of the chemical periodic table across billions of years of cosmic evolution. But the light year also reveals something deeply unsettling about the future of cosmic observation. Due to the accelerating expansion of space driven by dark energy, the observable universe is actually shrinking in terms of what future astronomers will be able to see. Galaxies that are currently visible to us are slowly being carried beyond the cosmic horizon as space expands faster than their light can travel to reach us. This means that astronomers living billions of years in the future will inhabit a much lonelier cosmos. They'll look out at a sky containing only the local group of galaxies, completely unaware of the vast cosmic web that we're privileged to observe today. The evidence for the Big Bang, cosmic expansion, and the true scale of the universe will have been stretched beyond detection. They'll have no way to discover that the universe is actually filled with hundreds of billions of other galaxies. Future civilizations will face a fundamental limitation on cosmic knowledge that we currently don't experience. They'll be cosmically isolated not by distance, but by the expansion of space itself. The light year will become an even more exclusive barrier, permitting observation of only the most local cosmic structures, while hiding the true magnitude of universal architecture. This creates a profound responsibility for current astronomers and scientists. We may be living during a unique window in cosmic history, when the universe reveals its true scale and structure. The observations we make today might represent humanity's only opportunity to understand the full scope of cosmic evolution and the complete inventory of universal contents. The psychological weight of this realization can be staggering. We're not just observers of the cosmos, we're witnesses to a cosmic revelation that may never be repeated. The universe is currently displaying its full majesty and complexity, but this cosmic transparency is temporary. Future intelligent beings may never have the opportunity to discover the true nature of the reality they inhabit. This temporal isolation extends beyond just astronomical observation. It affects every aspect of how conscious beings might relate to the cosmos across vast distances. The light year creates barriers not just to communication, but to shared experience, cultural exchange, and collective understanding. Each star system exists in its own bubble of causality, developing its own unique relationship with existence without the possibility of immediate feedback from cosmic neighbors. Consider how profoundly this isolation might affect the development of philosophy, science, and culture on worlds separated by light years of space. Without the ability to compare notes with other civilizations, each intelligent species must develop its own understanding of reality based solely on local observations and internal reasoning. The diversity of possible worldviews and conceptual frameworks could be staggering. Different civilizations might develop completely incompatible ways of understanding space, time, causality, and existence itself. What seems fundamental and obvious to us might be utterly alien to minds that evolved under different circumstances in distant star systems. The light year doesn't just separate us physically from potential cosmic neighbors, it isolates us conceptually and philosophically as well. Yet there's something beautiful about this cosmic diversity of perspective. Each world that develops consciousness represents a unique experiment in understanding reality. Every civilization that looks up at the stars brings its own evolutionary history, its own sensory capabilities, its own cognitive architecture to the task of comprehending the universe. The cosmos becomes a vast laboratory for exploring different approaches to knowledge and meaning. The light year ensures that these experiments in consciousness develop independently, without contamination from external influences. Each world must discover its own relationship with existence, develop its own science and philosophy, create its own art and culture in response to the cosmic environment it observes. The barriers imposed by light travel time become incubators for intellectual and cultural diversity on scales we can barely imagine. But perhaps the most profound aspect of light years is how they reveal the fundamental relationship between information and reality itself. Every photon that crosses cosmic distances is carrying information about its place and time of origin. This information doesn't just describe physical conditions like temperature and chemical composition. It carries deeper truths about the nature of space-time, the behavior of matter and energy, and the fundamental laws that govern cosmic evolution. When we observe distant galaxies, we're not just collecting light. We're gathering information that has been encoded in electromagnetic radiation and transmitted across the universe at the maximum possible speed. Each photon is like a data packet, carrying compressed information about cosmic conditions billions of years ago and billions of light years away. The universe reveals itself to be fundamentally information-based, in ways that challenge our intuitive understanding of matter and energy. Physical reality might be better understood as patterns of information propagating through space-time at the speed of light. The light year becomes not just a measure of distance, but a measure of how quickly reality can update itself, how fast information can flow from one location to another. This informational view of the cosmos transforms our understanding of what we're actually observing when we look at distant stars and galaxies. We're not just seeing objects in space. We're receiving data transmissions from across the universe, downloading information that has been traveling through space-time for eons to reach our telescopes and instruments. Every astronomical observation becomes an act of cosmic archaeology mixed with information science. We're decoding signals that have crossed unimaginable distances, extracting meaning from data streams that have been propagating through space longer than complex life has existed on Earth. The light year measures not just the spatial separation between cosmic transmitters and receivers, but the temporal delay in this universal information network. The more we contemplate these cosmic communication systems, the more we realize that consciousness itself might be the universe's way of processing and understanding the information that flows through it at light speed. We're not separate from the cosmos we observe. We're part of its information processing network, temporary arrangements of matter and energy that have achieved the remarkable capability of decoding and interpreting the signals that surround us. In this view, every conscious being becomes a node in a vast cosmic information network, connected to the rest of the universe through the patient propagation of light across space and time. The light year measures the bandwidth of this network, the rate at which cosmic information can flow from one conscious observer to another, but the network operates on timescales that dwarf human experience. Messages take years, centuries, millennia, or billions of years to propagate between nodes. The conversations occur so slowly that individual lifespans represent barely a whisper in the cosmic dialogue. Yet the conversations continue, carried forward by light that never stops traveling, information that never stops flowing, consciousness that never stops wondering about its place in the infinite expanse of space and time. As we drift deeper into contemplation of these light-year distances, we find ourselves confronting something that might be the ultimate truth about cosmic existence. We live in a universe where information travels at a finite speed, where knowledge has built-in delays, where understanding must be patient enough to wait for light to cross the vast distances between sources and observers. This isn't a limitation of our technology or a temporary barrier to be overcome by future innovations. It's a fundamental feature of reality itself, woven into the very structure of space-time. The light year represents the universe's own speed limit on knowledge, the cosmic constraint that ensures information cannot travel faster than causality can propagate. In accepting this limitation, we discover something profound about the nature of wisdom itself. True understanding of cosmic reality requires not just intelligence, but patience on scales that exceed human lifespans. The universe reveals its secrets slowly, across light years of space and eons of time, to observers willing to wait for ancient light to complete its journey across the cosmic dark. We are part of this patient cosmic conversation, temporary participants in a dialogue that began with the first stars and will continue long after our species has vanished from the cosmic stage. The light year measures not just the distances between stars, but the intervals between thoughts in the universe's long contemplation of itself. We exist within these cosmic thoughts, brief moments of awareness in a mind vast beyond comprehension, connected to the whole through threads of light that span the infinite reaches of space and time. The story of how we measure these impossible distances reads like humanity's greatest detective novel. For centuries, astronomers stared at points of light in the sky, with no way to determine whether they were looking at nearby candles or distant bonfires. The parallax method, one of our first breakthroughs in cosmic measurement, relies on something as simple as the apparent shift in stellar positions as Earth orbits the Sun. Picture holding your finger at arm's length and closing one eye, then the other. Your finger appears to jump back and forth against the distant background. This same principle allows us to measure distances to nearby stars by observing how they seem to shift against more distant stellar backgrounds as our planet completes its yearly journey around the Sun. The smaller the shift, the more distant the star. It's elegant geometry applied to cosmic scales, turning Earth's orbit into a cosmic measuring stick. But here's what makes this achievement truly extraordinary. The angular shifts we're measuring are almost incomprehensibly tiny. For Proxima Centauri, our nearest stellar neighbor, the parallax shift amounts to less than 1 arcsecond. To put that in perspective, an arcsecond is the angle subtended by a dime viewed from a distance of about 4 kilometers. We're measuring stellar positions to fractions of this already minuscule angle. The precision required for these measurements pushed the limits of human ingenuity for generations. Early astronomers spent decades trying to detect parallax shifts that were just beyond the reach of their instruments. Friedrich Bessel finally succeeded in 1838, measuring the distance to 61 Sugni and opening the door to our modern understanding of cosmic distances. His achievement represents one of those pivotal moments when human capability suddenly expanded to embrace a previously unknowable aspect of reality. From parallax measurements, astronomers developed increasingly sophisticated techniques for probing deeper into space. They discovered standard candles, objects whose intrinsic brightness is known, allowing distance calculations based on how dim they appear from Earth. Cepheid variable stars became cosmic lighthouses, their regular pulsations providing a reliable way to measure distances to nearby galaxies. Each new technique extended our reach further into the cosmos, while simultaneously revealing just how much farther we still had to go. The more we learned about cosmic distances, the more we realized how little we had previously understood about the true scale of existence. Every breakthrough in measurement techniques opened new vistas of space, while making clear that we had barely begun to explore the infinite reaches that surround us. Modern space-based telescopes have revolutionized our ability to measure cosmic distances with unprecedented precision. The Gaia mission has mapped the positions and motions of over 1 billion stars in our galaxy, creating the most detailed three-dimensional map of our cosmic neighborhood ever attempted. These measurements reveal not just where stars are located, but how they're moving through space, painting a dynamic picture of galactic motion that unfolds across millions of years. But the more precisely we measure these distances, the more we confront something that challenges our fundamental understanding of cosmic architecture. The universe appears to be expanding at an accelerating rate, driven by a mysterious force we call dark energy. This acceleration means that distant galaxies are moving away from us at ever-increasing speeds, stretching the very fabric of space itself. The implications of this discovery ripple through every aspect of how we understand cosmic distances. Objects that appear to be a certain distance away based on their light travel time are actually much farther away now, due to the expansion that has occurred during the light's journey to reach us. We're constantly recalibrating our cosmic maps as we discover new aspects of how space itself behaves on the largest scales. This expansion creates a dynamic relationship between distance and time that defies our everyday intuitions. When we observe a galaxy whose light has been traveling for 10 billion years to reach us, we're seeing it as it appeared in the distant past, but it's now much farther away than the distance its light has traveled. Space has been stretching the entire time, carrying that galaxy away from us, even as its ancient light continues its journey toward our telescopes. The mathematics of cosmic expansion reveals something truly mind-bending about the relationship between observation and reality. The most distant galaxies we can observe are receding from us faster than the speed of light, not because they're moving through space at such tremendous velocities, but because space itself is expanding at rates that exceed even the universe's ultimate speed limit. This creates regions of space that are forever beyond our ability to observe, not because they're too far away in any conventional sense, but because the expansion of space prevents their light from ever reaching us. We exist within a cosmic horizon that defines the boundary of the knowable universe, beyond which lies an infinite realm that remains permanently hidden from our view. The concept of cosmic horizons forces us to confront the relationship between knowledge and existence in the most fundamental way possible. There are galaxies out there, potentially countless numbers of them, whose light will never reach us, no matter how long we wait or how sensitive our instruments become. They exist in a realm that is not just practically unreachable, but theoretically unknowable. These hidden regions of space might contain phenomena that would revolutionize our understanding of physics, chemistry, and the possibilities for complexity in the universe. They might harbor forms of matter and energy that operate according to principles we've never encountered. They might contain structures and processes that would expand our conception of what's possible in cosmic evolution. Yet we are fundamentally prohibited from learning about any of it. The light year becomes not just a measure of distance, but a measure of the boundaries of possible knowledge. It defines the limits of what any observer, regardless of their technological capabilities or longevity, can ever discover about the universe they inhabit. This realization transforms our understanding of scientific inquiry itself. We're not just limited by our current instruments or theoretical frameworks. We're limited by the fundamental structure of space-time, by the relationship between information and causality, by the basic architecture of reality itself. The universe contains secrets that are not just currently unknown, but permanently unknowable. But there's something beautiful about these limitations. They ensure that the cosmos retains an element of mystery that no amount of technological advancement can eliminate. The universe will always be larger than our understanding, always contain realms that exist beyond the reach of observation, always maintain regions of space that preserve the possibility of the truly unknown. The light year also reveals something profound about the relationship between individual consciousness and cosmic reality. Each of us exists at the center of our own observable universe, our own sphere of potential knowledge defined by how far light has been able to travel since we began observing. But these spheres are not identical. An observer on a planet orbiting a star 1,000 light-years away would have access to completely different regions of cosmic space. Their observable universe would overlap with ours in some regions, while extending into areas we can never see. They might observe galaxies and cosmic phenomena that remain forever hidden from our perspective. The universe reveals different aspects of itself to different observers, ensuring that no single viewpoint can ever capture the complete cosmic picture. This multiplicity of cosmic perspectives suggests something remarkable about the nature of universal self-awareness. If consciousness exists elsewhere in the cosmos, each thinking being contributes a unique viewpoint to the universe's understanding of itself. The totality of cosmic knowledge becomes distributed across potentially countless observers, each adding their own piece to an infinite puzzle that can never be completed by any single perspective. The light-year measures not just the distances between these potential observers, but the gaps between different fragments of cosmic understanding. Each conscious being exists in their own informational bubble, connected to the rest of the universe through the patient propagation of light, but forever separated by barriers of space and time that ensure their experience of reality remains unique and irreplaceable. But perhaps the most profound implication of light-year distances is what they reveal about the nature of cosmic time itself. When we observe distant galaxies, we're not just looking across space, we're looking across time. The universe displays its entire history simultaneously, with nearby objects showing us recent cosmic conditions, while distant galaxies reveal ancient epochs of universal evolution. This creates a strange situation where the past and present coexist in our observations. We can simultaneously observe star formation as it occurs in nearby galaxies, and as it occurred billions of years ago in distant ones. We can study galactic evolution by comparing objects at different distances, effectively watching the same processes unfold across different epochs of cosmic time. The universe becomes a kind of time machine that allows us to observe directly the processes that shaped cosmic history. We can witness the formation of the first stars, the assembly of primordial galaxies, the gradual enrichment of space with heavy elements created in stellar cores. We can observe the universe learning how to create complexity, developing the chemical and physical conditions that eventually made planets and life possible. This temporal archaeology extends our understanding far beyond what would be possible if we could only observe the current state of the cosmos. Instead of inferring cosmic history from theoretical models, we can observe it directly by looking at objects whose light has been traveling for different lengths of time to reach us. The light year becomes our excavation tool, allowing us to dig deeper into cosmic time by observing objects at ever greater distances. But this same temporal displacement that enables cosmic archaeology also creates a profound sense of isolation. We can observe the universe's past, but we can never observe its present except in our immediate cosmic neighborhood. Everything we see beyond our local region of space represents ancient history, conditions that may have changed dramatically in the time it took for light to reach us. This temporal isolation means that our view of the cosmos is fundamentally incomplete. We're seeing a universe that no longer exists in the form we observe it. Stars may have died, galaxies may have collided, entire cosmic structures may have evolved beyond recognition, and we remain unaware of these changes because their light hasn't had time to reach us yet. The light year forces us to accept that cosmic knowledge is always historical, never contemporary. We can never know what's happening now in distant regions of space, because now has no meaning across cosmic distances. We can only know what was, preserved in ancient light that carries messages from across the vast reaches of space and time. In this patient contemplation of cosmic distances, we find ourselves confronting not just the scale of the universe, but the fundamental nature of existence itself. The light year reveals that we live in a cosmos where space and time are woven together in ways that challenge our most basic intuitions about reality. Distance becomes duration, observation becomes archaeology, and the present moment dissolves into layers of ancient light carrying messages from across the infinite expanse of cosmic history. As we continue to explore these mind-breaking distances, we discover that the light year isn't just a unit of measurement. It's a window into the deepest truths about the universe we inhabit, a revelation about the nature of space and time that transforms our understanding of what it means to exist in this vast, ancient, and eternally mysterious cosmos we call home. The more we study these cosmic distances, the more we realize that we're not just measuring space between objects. We're exploring the fundamental architecture of reality itself, discovering the rules that govern how information flows through the universe, how causality propagates across the cosmic web, and how consciousness relates to the infinite expanses that surround us on all sides. Perhaps the most extraordinary aspect of contemplating light years is how they force us to reconsider our relationship with time itself. We're accustomed to thinking of time as a river flowing steadily from past to future, carrying us along at a consistent pace. But cosmic distances reveal that time is far more fluid and relative than our earthbound experience suggests. When we observe a star explosion that occurred 50 light-years away, we're witnessing an event that happened 50 years ago according to our earthbound clocks. Yet from the perspective of light itself, that journey occurs in an instant. This creates a peculiar situation where different observers experience the same cosmic events at different moments in their personal timelines. An astronomer on Earth might observe a supernova explosion tonight, while a hypothetical observer, halfway between us and that dying star, would have witnessed the same event 25 years ago. The explosion itself occurred at a specific moment in cosmic time, but its observation is spread across decades of local time, depending on the observer's position in space. The relativity of cosmic observation becomes even more bewildering when we consider what happens to time itself at the speeds required to cross light-year distances. If we could somehow build a spacecraft capable of traveling at 99% of light speed, something that remains purely theoretical, time would slow dramatically for the travelers. A journey to a star 10 light-years away might take only a few months from the perspective of those aboard the spacecraft, while decades would pass on Earth. This time, dilation effect means that interstellar travel, if it ever becomes possible, would fundamentally alter the relationship between travelers and their home world. Astronauts returning from a journey to nearby stars would find themselves in a future Earth, having experienced only months or years while their planet aged by decades or centuries. They would become temporal refugees, displaced not just in space but in time itself. The psychological implications of such temporal displacement stretch our understanding of identity and belonging in ways that science fiction writers have only begun to explore. Imagine returning from a journey to Proxima Centauri to find that everyone you knew had aged decades while you remained relatively unchanged. Your children might be older than you remember being when you left. Your civilization might have evolved in ways that make you feel like a stranger in your own world. But these theoretical journeys pale in comparison to the temporal displacement we already experience simply by observing the cosmos from our stationary position on Earth. Every time we look up at the night sky, we're seeing a universe that exists across multiple epochs simultaneously. The North Star shows us conditions from 400 years ago, while the Andromeda Galaxy reveals its state from 2.5 million years in the past. Our view of the cosmos is essentially a time-lapse photograph of universal evolution, with different regions of space displaying different moments in cosmic history. This temporal layering of cosmic observation creates a unique form of scientific investigation that has no parallel in any other field of study. Geologists can examine rock strata to study Earth's history, but they're looking at evidence of past events preserved in present materials. Astronomers, by contrast, can observe past events directly as they unfold across the light years, watching ancient processes that are still propagating through space as electromagnetic radiation. The light from the most distant quasars we can observe began its journey when the universe was less than 1 billion years old, carrying information about cosmic conditions that existed when the first galaxies were forming through violent processes, unlike anything we observe in the present-day cosmos. These ancient beacons reveal a universe that was more chaotic, more energetic, and fundamentally different from the relatively calm cosmic environment we observe in our local neighborhood. By studying objects at different distances, we can essentially watch the universe grow up. We can observe how galaxies evolved from small, irregular collections of young stars into the massive spiral and elliptical structures we see today. We can witness the gradual enrichment of space with heavy elements created in stellar cores and scattered by supernovae. We can watch the universe learning how to create the chemical complexity that eventually made planets and life possible. This cosmic time machine reveals that the universe has a biography, a personal history of growth and change that we can read directly in the light that surrounds us. Every photon carries within it information about the cosmic epoch from which it originated. The spectrum of ancient starlight tells us about stellar temperatures and chemical compositions that existed billions of years ago. The patterns of absorption and emission reveal the physics and chemistry of a younger cosmos. But the more we study this cosmic biography, the more we realize how much of the story remains hidden from our view. The light-year distances that enable our temporal archaeology also limit how much of cosmic history we can ever observe. There are epochs of universal evolution that occurred too recently for their light to have reached us from the most distant galaxies. There are regions of space whose current state will never be observable because they're receding faster than light can travel through expanding space. This creates a fundamental asymmetry in cosmic knowledge. We can observe the universe's past with increasing clarity as our instruments improve, but we can never observe its present except in our immediate cosmic neighborhood. The future remains completely hidden, not just because it hasn't happened yet, but because even when it does occur in distant regions, the information about those future events may never be able to reach us due to cosmic expansion. The accelerating expansion of space, driven by dark energy, means that our observable universe is actually shrinking in terms of what we'll be able to see in the future. Galaxies currently visible to us are slowly slipping beyond our cosmic horizon as space expands faster than their light can travel to reach us. We're living during a unique epoch in cosmic history when the universe displays its full scale and complexity. Future civilizations will inhabit a lonelier cosmos, where the evidence for the Big Bang and cosmic expansion has been stretched beyond detection. This temporal privilege carries with it a profound responsibility. We may be among the last observers in cosmic history who can witness the universe in its full glory. The measurements we make today, the photographs we capture of distant galaxies, the spectra we analyze of ancient quasars, may represent the only record of cosmic phenomena that will gradually disappear from view as expansion continues. The light year becomes not just a measure of distance, but a measure of cosmic opportunity. Every light year we can observe represents a piece of universal history that may not remain visible forever. We're engaged in a race against cosmic expansion, trying to map and understand the full scope of the universe before it slips beyond our ability to study. This urgency adds a poignant dimension to astronomical research. Every new discovery about distant galaxies and ancient cosmic processes contributes to a database of knowledge that may be irreplaceable. We're creating an archive of cosmic information for future generations, who will inhabit a universe where such distant observations are no longer possible. The psychological weight of this cosmic responsibility can be overwhelming. We're not just casual observers of the universe, we're witnesses to a cosmic revelation that is gradually ending. The universe is currently displaying its autobiography in the light that surrounds us. But this transparency is temporary. The pages of cosmic history are slowly being turned, and once they pass beyond our observational horizon, they may never be readable again. Yet there's something beautiful about our temporary role as cosmic historians. We exist during a brief window when the universe chooses to reveal its deepest secrets, when the light years that separate us from distant galaxies carry information rather than just empty space. We're privileged to witness the full scope of cosmic evolution, from the formation of the first stars to the assembly of galaxy clusters across billions of years of universal development. This privilege transforms astronomical observation from mere scientific curiosity into something approaching cosmic archaeology mixed with temporal anthropology. We're not just studying distant objects, we're documenting the biography of existence itself. Every spectrum we analyze, every image we capture, every measurement we make contributes to humanity's attempt to understand the complete story of how complexity emerged from simplicity across the vast scales of space and time. The light year serves as our primary tool in this cosmic investigation, measuring not just distances, but epochs, not just separations, but the intervals between different chapters in the universe's long story. Each additional light year we can observe extends our reach further back into cosmic time, revealing earlier chapters in the universal narrative that connects the Big Bang to the emergence of stars, galaxies, planets, and ultimately consciousness itself. In contemplating these vast distances and the temporal archaeology they enable, we find ourselves confronting something that might be the most profound truth about human existence. We're not separate from the cosmic story we're studying. We're part of it. The atoms in our bodies were forged in stellar cores that exploded across the light years billions of years ago. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were created in nuclear furnaces whose light traveled across space for eons before the elements they scattered eventually found their way into the chemistry that makes our existence possible. We are literally made of ancient starlight, temporary arrangements of cosmic material that have achieved the remarkable feat of consciousness. The same light-year distances that separate us from distant stars also connect us to them through the elements they created and dispersed across space. We're not observers of the cosmic story, we're characters in it, brief moments of self-awareness in a universe that has been unfolding for nearly 14 billion years. The light year reveals that our relationship with the cosmos is fundamentally intimate, despite the vast distances involved. Every photon that enters our eyes has crossed space specifically to reach us, carrying information about its cosmic journey directly to our consciousness. We're connected to distant stars and galaxies through threads of light that span the universe, participants in a cosmic communication network that operates at the speed of light across distances that break our brains, but somehow still manage to connect us to the infinite expanse we call home. In this gentle contemplation of cosmic distances, we discover that the light year isn't just a measurement of space. It's a measurement of connection, of communication, of the fundamental relationships that bind consciousness to cosmos across the vast reaches of space and time. We exist within this network of ancient light, temporary nodes of awareness in a universe that reveals itself through patient observation of distances so vast they challenge everything we thought we knew about the nature of existence itself. The story continues across the light years, written in electromagnetic radiation that carries the autobiography of the universe to any consciousness willing to look up at the night sky and wonder about the impossible distances that separate and connect us to the infinite cosmos that surrounds us on every side. And so we find ourselves at the end of this cosmic journey, having traveled through distances that truly do break our brains in the most beautiful way possible. We've explored how a single light year stretches our understanding beyond its limits, how the space between stars creates islands of existence separated by gulfs of time itself, and how every photon reaching our eyes tonight has crossed impossible distances to deliver its ancient message directly to our consciousness. Sweet dreams, fellow cosmic wanderers, and remember that you are made of starlight.